Consensus is something that is at the very core. It's a technical topic, but it's at the very core of blockchain and distributed systems in general. It's similar to, I don't know, physics, gravity, or friction. It's really core part of the universe. And we don't deal with it every day because the blockchain takes care of us, takes care of the problem for us. In fact, you can think of the blockchain as a layer that hides the consensus from you and solves it for you and gives you a layer of incentive for a large number of people to collectively solve consensus, and you can build on top of it. But let's look under that layer of abstraction to what actually consensus is. So this was my topic of master thesis over 10 years ago. So I'm a little rusty, but let's try to do this. So the way consensus is generally explained first is with the two generals problem. And let's play this game. So you have two generals, and they basically want to storm a castle. And right now, the two generals are hiding on two different sides of the castle. This general came north, and he's hiding in the hills. This other general is hiding in the forest. So here's the tricky thing. They need to attack at the same time. If they attack separately, they will be slaughtered and the castle will stand up. If they attack at the same time, they will win. Okay? So how do we get those two generals to attack at the same time? Well, they're hidden. They cannot just shout out to each other. So they could do something like send each other messenger pigeons. Now I'm gonna do a very bad attempt to draw a bird.
I can only see your right generals.
I thought I marked the board well. Ooh. How about this?
That's perfect. There we go.
So yeah, so let's say we have a messenger pigeon, and General 1 sends a messenger pigeon to General 2, and it says, let's attack at midnight tonight. That seems to work, but what if the pigeon gets lost? Then the first general will attack, the second one never received the message, so it won't attack, and the first general dies, and we're screwed. So we can play this game with pigeons and say, okay, the first general sends a pigeon, the second general responds with a different pigeon, but you could say that the second pigeon gets lost. And so General 2 attacks, General 1 didn't receive the read receipt, it won't attack, it will die. You basically relatively easy can add and add and add pigeons, but you won't solve the problem because basically one of the pigeon gets lost, you're screwed. And it doesn't even change if you add more pigeons. So this general could send 100 pigeons, but like the rules of the game are now, it's basically an impossible problem. You cannot guarantee that the two generals at the moment of attacking will agree on whether to attack or not. And this is the fundamental law of the universe in distributed systems. You cannot agree on the value of a certain thing at a certain moment in time. Just to prove this even more, let's forget about pigeon. Let's give our generals iMessage. So you send messages every day with people, and you might think, oh, if they just had iMessage, they would not have this problem. But iMessage is in fact as reliable as pigeons, meaning it's a lot more reliable, it's a lot faster, but there's no guarantee that a message will get to the other end within a given time. Just imagine your other general dropped his phone in the toilet, boom, message is not delivered. You know, there's an infinity of situations where a message can be lost or arbitrarily delayed. So this is an impossible problem. And if we translate this problem into the computer domain, we have a pretty grim result, which is if you take two computers and you try to make them agree on the value of a single bit at any moment in time, you can't. It's impossible. If you try to say, hey, these two computers at 5 o'clock today, they will agree whether this bit value is 1 or 0, there is simply no way to guarantee that that will be the case. You might be lucky and be right and let them, they will be able to agree on it 99.9% of the cases, but there's no protocol that guarantees that they will. And so this seems hopeless. We cannot even get two computers to agree on the value of a single bit. That seems like it doesn't fit with the reality that we have today, where we use computers to do everything. And so there's two forks in the road here. The impossibility result stays, but we can take two approaches. One is the probabilistic approach. So maybe we don't have a protocol that mathematically guarantees that two computers or two people can agree, but we can build a protocol where we're 99.999% sure that the two will agree. So this is, for example, the approach taken with, I don't know, online real-time video games. So you cannot guarantee that your message of I hit this other player will be delivered in time and received and processed by the rest of the players. But guaranteeing that most of the time the message is delivered is good enough. Because what's the worst that can happen? Somebody that doesn't get hit, or somebody's get hit a little bit later, you have a little bit of lag. In this kind of system, it's fine. And it's the same for iMessage. You cannot consistently deliver and guarantee that your message will be delivered within X seconds, but for most of the time it's fine. Eventually, the message is going to get to the other end, and you can talk to people pretty reliably. So this is a probabilistic solution, though, and it's not good enough for banks, for example. You cannot say, I guarantee that 99.99 of the time your transaction will go through, but 0.1% of the time your money will be lost in transit. That's absolutely not acceptable for a bank. And same thing for blockchain. Imagine that 0.1% of your transaction gets lost. The money or the token gets removed from your account but doesn't get added to the other account. If you have 10 million transactions per day, that's a huge number of things that you lost into the void. And that's absolutely not acceptable. So for this kind of system, the probabilistic approach does not work. We need something much stronger. And so in this domain, we basically decide to solve this problem by giving up the time guarantees. So the two generals cannot agree on attacking at midnight. Let's relax the midnight requirement. Let's stop to act at the same time and instead decide that eventually the two generals will agree on what to do. And so this brings us into the world of eventual consistency, where we stop trying to agree on the value of a bit at a given time, and instead we try to agree on the value of the bit and the subsequent value of a bit in the same order. So we don't try to control when we're going to see the value, but we know that we were going to see same value that everybody else is seeing eventually. For example, when our internet is back up, or when the phone is taken out of the toilet and dried up and works again, then we will receive the messages that we missed during the time we were offline. So nobody can say, I delivered that message to you within at a certain time, but eventually we will see all the messages that everyone else is seeing. And so this kind of approach to solving consensus, again, eventual consistency, there are different ways to approach it, but it's the path taken by blockchain for the most part. Blockchain, what it does is basically called distributed or replicated state machine approach, where you have a computer somewhere, it starts with an empty state. You have a different computer somewhere else starting with empty state. These are all of your nodes. And what we guarantee is that we will send the same set of updates in the same order to all of these computers. So at any moment in time, they might not be at the same transaction, but they will go through the same exact sequence of steps. And therefore, if you give it enough time, they will all reach the same end state. And yeah, this is the path taken by, for example, Ethereum or other blockchains where not all of them, but the one that have a general centralized public ledger that everybody's interacting on the same ledger, all the nodes see the same sequence of steps. Now, Ethereum 2 is running into obvious scalability problem with this approach, and this is what the sharding is going to do. So you don't have a complete replica of the entire blockchain on every node. You can start sharding, and now you need rules of consistency between shards, but it's still pretty similar. And so going back to the beginning, we couldn't solve the two general problem, and this was the easy version. If you introduce Byzantine generals, meaning generals that are actually enemies in disguise, it gets a lot more complex. But at least we came up with a scheme so that we can guarantee that given enough time, all of us will see the same state of the system. And this is the basis upon which blockchain is built, because we all see the same system. It's like a giant public database. We can interact with it and transfer things and do things and coordinate.